Good morning, everyone. Some reminders. Doing Lorentzian geometry, so at each tangent space we have a Lorentzian metric tensor. It defines vectors which are time-like future pointing. So time-like would be negative length or past pointing, and so we decided we need to know that we can do this globally. That's a space-time. Null vectors would be at the boundary of this. Null vectors have zero length, but are not zero, right? So they're avoiding the 0 point, and so you have null future pointing, null past pointing would be at this boundary here. A curve is a time-like future pointing or past pointing if it is piecewise C1. And so we can think of this like that. And the tangent to the curve should be time-like, well, either everywhere future directed or either everywhere past directed. And at the junction points, it also should be one-sided time-like. And the curve is causal if it's locally Lipschitz. Locally Lipschitz means that gamma dot is defined almost everywhere. And then you're asking that the gamma dot will be causal almost everywhere, again, consistently oriented. So once we have curves like that, you can think of a curve which is you go null here, go null here, go null here, go null here, and it can have a lot of these things. It can be weird, right? So causal curves can be weird, but I'm certainly almost everywhere differentiable, and tangent is causal. So the chronological future of a point so you take all the points which are lying on a time-like curve starting at P, right? So and either plus is for future directed, minus is for past directed. So I drew something like that. But this is not clear, right? Somebody mentioned this is not clear, and that's something certainly that needs explaining, that it does look like that. J plus would be same, but now this is the causal future. Well, the future being with plus, of course, and the chronological past will be with the minus. Okay. And so these are causal past and future. And let's see, so now, given a set omega, we can also define A plus minus of omega is this union over P and omega, I plus or minus of P, and obvious equivalent definition for J, which I'm going to write down. So this is what we defined last time. And so let's say Minkowski space-time, it's not very difficult to prove that if you have a point, then if you think about points in Minkowski spacetime as being vectors, which they are not, because Minkowski spacetime is not a vector space but a manifold. But if you think about points in Minkowski spacetime as being vectors, then the I plus of this point P would be actually the set of time-like vectors from P, and that's not obvious. This has to be, it's not very difficult to prove, but this has to be proved, right? So in other words, if you are in Minkowski, you look at the set of points which are on causal curves, then of course you can go to a point from here to this one on just following a straight line. So you get a time-like curve from here to there. So obviously this set is included, but then you need to show that it's not larger, right? So, and indeed you can show that that's how it looks like. So J plus of P, so the boundary of I plus of P will be the same as the boundary of J plus, and will be just null geodesics, so set covered by null geodesics. So in Minkowski spacetime, just straight lines, set covered by null geodesics, null future directed geodesics. Starting from P. So whether manifold or just tangent space, picture is the same. And in general, if you're on a smooth manifold, this remains true locally. And locally means the following, that you take a point, that there exists a neighborhood of this point in which this looks like that. For Lipschitz metrics. So there is a threshold here. So certainly for smooth metrics, this looks like that. So for smooth metrics, you'll have a set covered by, you know what null future directed geodesics starting from this point mean. And that would be how this set would look like locally. Well, if the metric is C2, then if you think about the geodesic equation, so G is in C2, the geodesic equation is D2 over dx plus gamma P dot, gamma x dot equals 0. Then this is an ODE. Metric is C2. The Christophers would be C1. Cauchy-Lipschitz theorem. Geodesics exist, are well defined, are unique. And so, you know, these things exist and are unique, then the statement is exactly the same. If the metric is C11, still works, because gamma will be Lipschitz, and then again, Cauchy-Lipschitz theorem, geodesics exist, are unique, so you still have this problem. Now the question is, what happens below? And actually, the threshold is not C11, but is Lipschitz. So of course, there's this gray zone where it actually requires a little more work to prove this. But let me mention the following, right? That the key part saying that there exist metrics which are Hölder continuous, for which the picture is different. And actually, this would be something which looks like that you have a point P, and then you have it's still a set which kind of is bounded the same way, but there is maybe a gray region here, and another one here, so that this is I plus of T, and the boundary of dj plus of P is here. So there is some weird region which can be reached by causal curves starting from P, but not by time-like ones. Yes?
Do you assume that
No. No, right, exactly, right? So there is, as I said, there is a gray zone between Lipschitz and C11. But I mean, this set is well defined. This is my definition out there, right? You can reach. So the points here inside are the ones which can be reached on a piecewise differential curve, and the closed thing is actually the set where which can be reached by Lipschitz curves, right? Which are almost everywhere. Right? So you can talk about geodesics as curves which lie on the boundary on this set. That would be the natural definition. But I don't think anyone has really worked out what would be the optimal definition here. There's a definition in the case of Filipov that people have been using here. So, right. So if the metric is Lipschitz, so C01, then the Christophers would be and infinity. So defined almost everywhere and bounded. And in this case, there's something called Lipschitz, Philip of geodesics, which we can use here. But no, I mean, that's why I said it's local, right? Locally.
Okay, you have a local coordinate C.
Right.
Do you assume any?
But the manifold is always smooth in my case.
Okay.
Right. But then, of course, once you're working with metrics which are not smooth, it might be convenient to work with coordinates which are not smooth for some reasons, right? So that's fine too. But I mean, then being a metric being Lipschitz means that there exists a coordinate system in which it is Lipschitz, right? And then the class of coordinate systems under which this is invariant is actually much wider than smooth changes. I mean, any C11 changes of coordinates will preserve this, so it can work with such coordinates. For this proof? Yes. No, this is a variations of curves argument. And it really has to do with the differentiability of the metric in this coordinate system.
Just let me try again. And statements, I mean, it probably works on connection, but one problem of finding like geodesic.
I don't know. Maybe, yeah, that's an interesting suggestion. I've always been interested how to define this kind of boundaries. I mean, if you're in such situation, right, there's an obvious boundary, which is this one, and there's an obvious boundary, which is this one. But how can you intrinsically define them without knowing the sets, right? But by looking at curves, yeah, it's just, so maybe something like that could be interesting. Yeah. I don't know. So in any case, so these are these bubbly space-time where the boundary of the future, of the causal future, is not the closure of the boundary of the time-like future. And I think that this example started the whole industry and interest in these more general Lorentzian geometries, which are not smooth but synthetic and things like that. So that's kind of something which was not obvious at all, right? It's something like that can exist, right? So this is the and what's happening here that you have this this metric, you can write a metric like this, which is piecewise smooth. So you know exactly what a geodesic is, except it's only Lipschitz on the surface, and then the geodesics, if you take the surface, they will be just bifurcating from it, right? So you get this family of bifurcating geodesics, and it's going to fill out this region here and covers J+ of P. So no curves which are geodesics, well, whatever this means, because this metric, I mean, as long as they leave this curve, they're geodesics in the normal sense. So that's good. Good, but this is local. So what about global? So let's say, we say that a space-time Mg is chronological if it does not contain closed time-like curves. Closed, and closed in the sense coming back to itself, right? Closed time-like curves. And we say that Mg is causal if it does not contain closed causal curves. Now, in physics, you don't want to have causal time-like curves. You don't want to have causal curves because closed causal curves because you think that time-like curves. So let's step back. Being time-like means that you're moving with velocity less than the speed of light. This is an experimental fact. We've never seen any objects moving faster than the speed of light. And it's an axiom of nowadays physics. There is no such thing. Of course, if you start putting in quantum physics, that's a different story. This becomes much more trickier because you've certainly heard of this kind of, well, Nobel Prize winning experiments where you do quantum manipulations. And if you know that something happens here, you know immediately what happens there. So in some sense, causality in quantum theory is a mysterious thing. Those people who claim to understand quantum physics say there is no issue. Causality is preserved in quantum mechanics. I don't understand quantum mechanics, and I don't understand why it's preserved. But in any case, that's an experimental fact, right? So you can measure this correlation. You know that state of a quantum system is something here, then you know immediately what it is here. And because it's probabilistic, you didn't know what it was before you did the measurement. So, so somehow this causality in quantum mechanics is a tricky thing, but in classical physics, we just take it for granted. No physical object can move faster than light, and therefore massive physical objects move on time-like causal curves, time-like future-directed. Unfortunately, we can't go back. In the past would be nice sometimes, just to go a little back to the past. We don't know a mechanism to do this. So future-directed is your enemy here, and causal is by taking closures, right, or approximating, or light, right? So massless objects can move on causal path, but so in particular, if you have a closed time-like curve, right, then you just travel to the future, come back where you started. That would be great. If you came back and you were younger again, if you come back and you're older, maybe that's not that great anywhere. But maybe you could just come back to the place where you started and influence what you were doing when you were young and stupid with the experience. So we don't know a way of doing this. So the axiom in physics, we don't want that, right? So we don't want such spacetimes. And of course, so can this happen? Of course, it can happen. So just take an example of something which is not chronological. This is an obvious one. Chronological. So just take a metric G is equal minus d phi squared plus anything. So let's say d plus flat or any metric, any G Riemannian. So this is gamma, where gamma is Riemannian. And phi is on a circle, right? So E to E phi is in S1. So phi is periodic, right? So just you can think of this as being a slab like that, where you identify phi equals 0 with phi equal 2 pi. And yeah, so you just go up in time. So you take the curve gamma of S is phi equal S, and the other are constant. So these are coordinates on this transverse manifold. The tangent is gamma dot is just d phi. The length of d phi is minus 1. Right? So this is obviously a time-like curve, and it closes on itself. So we don't want things like that. Obviously, if it's not chronological, it's not causal either, right? Because time-like curves are causal curves. So it's not causal. What is a little more interesting to prove is to take an example which is chronological but not causal. And that's a nice example to think about. It introduces important notions. So let me go through it in detail. chronological but not causal. So we're going to take a metric which is, just let's make it two-dimensional. So let's see, minus dt dx plus t square d phi square. So t will be in R, and e to e phi is in a circle, right? So if you look at constant t, then you get circles. And so in space, the topology is a circle, and thank you. Yeah. Good. So this is my metric. Now, so is this Lorentzian to start with? Well, let's calculate the matrix which goes with this is just no dt square, right? So G mu Nuri, if you're not familiar with this, then you just take the scalar product of the basis vectors, right? So you take the scalar product of vector t with itself. There's no dt square here, so it's 0. Scalar product with put a t here. A scalar product with dt d phi will be -1. There's a 2 here because there are 2 -1s. And the scalar product with d phi with itself will be t squared. Right? So this is the matrix. The determinant is 0 -1. So it is a Lorentzian matrix, right? So 2 path 2, determinant -1, it can only be Lorentzian. Signature is minus, if the signature were minus minus, the determinant would be positive, right? So it must be minus plus or plus minus. And so so one of the directions is time, one is space. And good, so this is the picture. And now if you look at the curve, gamma of S is equal, t equals 0, and phi is equal S, then what is the length of so the tangent is d phi, and this is the length of d phi, so g of gamma dot is t squared. So this is a nice space-like curve, except at t equals 0, right? So at t equals 0, we get a curve which is, well, obviously tangent is non-zero. Obviously the length of the tangent is 0, so it's a causal curve. Whether it's future and past directed, well, you make your choice, but in any case, it's a causal curve with some choice of time orientation, be causal future oriented or causal past oriented. Make a choice so that phi dot, right, on this curve, then it's future directed, say, but it's still a causality problem. If you have a closed past directed time-like curve or causal curve, you go backwards, you're going to get a future directed, right? Because going backwards on a curve changes the sign of the tangent. So, so this time orientation doesn't matter here. So this is obviously not causal, right? This is not a causal space-time. And so now, is it chronological? Well, the statement is it's actually not chronological. It is chronological, sorry. So there are no closed time-like curves. Well, it should be kind of obvious. And morally, the way it goes is as follows. There's something which is called time functions. So a time function is something which increases on causal curves. So I'm going to define this. And t is actually a time function in this region. And t is a time function in this region. So in other words, if you have a causal curve, t would increase on this curve here. So there can't be a closed time-like curve here. T would increase on a on a causal curve here. So there can't be a closed causal time-like curve here either. So the only thing would be a time-like curve which goes up, crosses, and comes back. But it can't either, because once it crossed, it has to continue upwards, okay? So the key here to prove this is existence of notion of time functions. And this is a notion which has been introduced by known Viennese mathematician called Kurt Gödel, when he was interested in notion of time in Einstein's theory, and wrote down his solutions, which are an example of solutions which violate this chronology condition. So that was kind of one of the first paper which was showing that Einstein equations, so you get a solution of Einstein equations, perfectly reasonable matter fields, which has causality problems. Of course, Minkowski spacetime with this identification is a perfectly reasonable solution of Einstein equations. It's but with causality violation. But here you feel that you're cheating, right? We can just undo this identification and you get something where things like that happen. Well, you can't undo this in the Gödel spacetime. So time function. What is a time function? So let's say for the purpose of say differentiable, you can just differentiable function with gradient. Well, actually, time-like. And when you're saying time-like, you can think, well, future pointing or past pointing. With my signature, you want it past pointing, right? So time-like, past pointing. So this time function is useful to understand the geometry of black holes as well, to which we'll come in the next lecture, maybe even today, probably not today, but in the next lecture. So, right. So, and okay, so an example would be, of course, the T in Minkowski spacetime, in Minkowski. And so what is, of course, the differential? So what's the gradient, right? So grad T is, you just take the inverse metric and take the differential and make a vector out of it. So we just take G to be the Minkowski metric. Then the covariant metric is this matrix that you're all familiar with, which also means that the inverse metric is has a -1 here. G mu nu would have a -1 here, and the inverse metric is what you need in this equation, right? So then so you differentiate T, you only get a zero entry, right? So grad T in Minkowski would be eta mu 0 d mu, right? Because the differential of T, you get only the 0 entry, and because the metric is, so this is minus dt, okay? So that's this minus here, which is coming from this minus here, is why I want past here. Okay. If one uses the plus minus 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 convention, where many physics textbooks do, just a comment on this. Why am I using minus plus 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 and not plus minus minus minus? If you're doing particle physics, you want to use plus minus 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 here, because it has to do with the energy momentum and mass. So the mass of a moving object, you define the length of the tangent vector. It's time-like, so for a time-like vector, for me would be would have negative lengths, where they want positive one, right? So plus square would be like that. So it's convenient to have a plus here, but then when you're doing the Cauchy problem in general relativity, to which I'll come in my last lecture, then this part of the metric will be the metric induced on the level sets of T, and you want this to be Riemannian, not minus Riemannian. So that's most mathematical relativists use this minus plus 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 signature, but a lot of literature uses plus minus minus minus. So if you were in the other convention, you would probably ask for time-like future pointing. And also the fact is that the time functions are strictly increasing along causal curves, causal future directed. And I'm going to causal future directed curves. And the proof is very simple, so let me just do it. So the first lemma is that if you have two vectors, if x is time-like future pointing, past pointing, sorry, and y is causal future pointing, then its scalar product is positive. Larger than 0. So maybe let's just assume this lemma and see how this continues. So in other words, if I take two vectors, x is here, time-like, and actually time-like past pointing, this is going to be the gradient of my time function. Y is causal future pointing. So maybe y could be actually on the boundary here even, right? So here or here. But this one is in the interior, so this is x. And the scalar product of such vectors has a sign. So this is one version of the statement is something called the inverse Cauchy-Schwarz inequality. So you can just, but in any case, if we assume this, then the proof that time functions increase on causal curves is just two equalities. So we take a causal curve and say it's actually C1, but of course, otherwise we could just look at it at points almost everywhere. Then if you calculate dt over ds, so gamma s is causal, and say C1, or at a differentiable point. dt over ds, well, this is, in other words, t composed with gamma, right? That's what I mean. Then this is the same as gamma dot mu dt over dx mu. And but this is the same as the scalar product of gamma dot with the gradient of t. And this is positive by the lemma. Okay, so that's the end of the proof. And the proof of the lemma, so this is and then, so if you have a general causal curve, this holds almost everywhere, and because the Lipschitz curves integrate their derivative, then this remains true for causal curves. And the proof of the lemma is just elementary Lorentzian geometry, and so let's do it. So if x is time-like past pointing, we can choose an orthonormal frame. So that, so say E mu, so that x is just proportional to the first element of the frame. And because it's path pointing, and I usually want my frames to be well-oriented, x0 should be negative. And well, in this frame, we can write y is equal y0 e0 plus yi ei, summation convention. So this is summed over i's. And y is future pointing, so y0 is positive. And then I just take a scalar product, g of x, y. Well, this is an orthonormal frame. So this is just the same as the Minkowski scalar product, minus x0, a0 plus x1, y1 plus xn, yn. My x's are all 0. So this is 0. This is negative. This is positive. So this is all positive. Okay, good. So that's the time function story. So it's a very simple notion, very simple observation. And we say that now a definition. Well, okay, so let's go back to our example now, so which I erased. So the metric now return to this to the example. The metric was minus 2 d t d phi plus t square d phi square. So let's look at the function t, right? So function t, if I look at the gradient of t, so this is, well, g mu nu, take the inverse metric. Well, actually, I can just do it. Let me do it slowly. So g mu nu, d mu t, d mu t. So, okay, so, well, let me just do it like that. So g mu nu. What's this gradient here? This is g mu sigma d sigma t d mu t. Okay. Now, this is the inverse matrix to this one. So this, by definition, is of the inverse matrix is just the identity matrix. So in other words, the identity matrix replaces sigma by nu. So this is d nu t, d nu t. And let me continue this calculation. Put an inverse matrix here, g nu alpha, d alpha t, d nu t. Now, of course, d nu t, just this is the first coordinate. So if you say that t is x0 and phi is x1, then this inserts a 0, 0 index. So this is the same as g0, 0, okay? So the length of the gradient of a coordinate, say first coordinates, is just the 0, 0 entry of the inverse matrix. That's the bottom line of this calculation. What is the inverse matrix here? So the inverse metric, or metric on the cotangent space. So the metric is out there. So the matrix, written in matrix form, there's no t square minus 1. We already had this on the board, t square. So the inverse matrix would be not too difficult to calculate. Then you guess it's probably something like that, t square 0, 1, 1, or something like that. This should be the matrix inverse to this one, right? So the determinant is minus 1 here. The determinant is minus 1 here, so at least at the level determinant it works. And probably if you check the products this time, that gives you minus one. This times that gives you a 1. This times this gives 0. This times that doesn't work. What am I doing wrong? Maybe here, right? Does this work better? Maybe this works, right? Let's see. This time, this gives a minus 1 here. So there are a few options. Maybe someone can save me here and tell me what the inverse matrix is. This is a good one? Thanks. Okay, this time this is minus 1, 1 is 1. This times this zeros, so they get zeros. And then, yeah, it's important that this has here opposite signs, so that cancel out, right? So plus t squared minus t squared. So this is the inverse matrix, which means that, and that's what we want, that means that G00 is minus t squared. And so the gradient of t is time-like, except that t equals 0, right? So time-like, except that t equals 0. So if we go back to this picture, and we say, well, what if I had a closed causal time-like curve, causal curve here? Time would have to increase on this curve. This is our lemma. But you're coming back to yourself, right? So you can't come back to yourself. Think of Lyapunov functionals, right? Lyapunov functionals when you're doing ODEs. Things would decrease along the things you're interested in. So you can't have a closed curve here. You can't have a closed one here because time only increases on causal curves. And if you crossed, you'd have to come back, but you cannot come back because once you've crossed, you have to increase. The only possibility would be that you come here, stay on this, and come back. But that's not possible because this circle is null, right? So this would not be a time-like curve. So that's the proof that these things are, that this space-time is not causal, but chronological. Good. So definitions. Mg is stably causal if it admits a time function. And I'm just mentioning this because I will not be using this condition if there exists a time function. So obviously, Minkowski spacetime is stably causal. So this is a parenthesis, but the key definition that I want is Mg is globally hyperbolic if it's causal and the causal diamonds are compact for every PQ. So you take 2 points P and Q. You look at the past of this point. You look at the future of this one. So let's see. So this would be the past of P intersected with the future of Q is compact. So that's the definition of global hyperbolicity. And that's the right notion to do Lorentzian geometry. You don't want anything less and anything more. One reason why this is a good notion is that you can do PDEs in spacetime like that, right? So in globally hyperbolic spacetime, linear wave equations have a well-posed Cauchy problem. Now, what does it have to do with the Cauchy problem? Well, that's one of the fundamental problems here, is that if Mg, and this is a theorem which essentially goes to Geroch, if Mg is globally hyperbolic, is globally hyperbolic. Then there exists a time function, so it's stably causal. Exists a time function, the level sets of which are Cauchy surfaces. And I didn't tell you what a Cauchy surface is, so let me just do it right now. And a Cauchy surface is a surface which is intersected by every inextendable causal curve precisely once. So i.e. Surfaces is the property for every inextendable causal curve intersects the surface precisely once. So maybe just a fact that the wave equation, there is a box G T is equal to 0, or say, maybe you could have lower order terms, have the Cauchy problem for this equation. For this equation, so phi equals 0 has unique, has, well, both existence and uniqueness for the equation is well posed. If the metric is smooth, and of course this can be weakened, but let me just not start discussing this. Certainly it's not well posed for Hölder metrics, so that's is well posed for G infinity. So i.e. for every Cauchy data on a Cauchy surface. A Cauchy surface is the surface which has the property that every inextendable causal curve intersects the surface precisely one. So for every Cauchy data on a Cauchy surface sigma, so what are the Cauchy data? For this case, phi at sigma would be part of the data, and say normal derivative. That would be Cauchy data for this. And this could be a tensor field, doesn't have to be a scalar field. And it could have lower order terms as well. Well, this has global solutions and unique global solutions, right? So that's well posed as global unique solutions. I'm out of time. Global unique solutions, and which depend continuously upon the data. Depend continuously. Good. So this is this closes what I wanted to say about causality theories. Is something about something called strong cosmic censorship, which I would discuss in this context next time, but I don't want to use more of your time at this stage. So